Hey everyone, and welcome. Today, we're diving deep and pulling back the curtain on the magic happening inside your pocket and on your desk. This is how computers really work, from a simple switch to a smart device. So let's kick things off with a question. Think about your smartphone for a second. All of its power, all its complexity. Now, what could it possibly have in common with a plain old light switch on the wall? The answer is, well, it's pretty much everything.
Believe it or not, it all boils down to this. Both of them operate on the simplest language you can imagine, a language with only two words, on and off. That's it. This one simple idea is the key to unlocking this whole topic.
Now, this simple on-off language has a proper name. It's the alphabet for every digital device out there, and it's called binary. It's all about speaking in ones and zeros. You and I, we live in what's called a decimal world. We use 10 different symbols, 0 through 9, to write down any number we can think of. Computers, though, they keep things way, way simpler. They only use two symbols, a 0 and a 1. So why only two? Well, it really just comes down to physics. Inside an electronic circuit, it's super easy and reliable to check for just two states. Is there a high voltage or isn't there? We call that high voltage a 1 and the low or non-existent voltage a 0. Simple, clean, and incredibly fast. And every single one of those ones or zeros is the absolute smallest piece of information a computer can understand. It's called a bit, which is short for binary digit. You can think of a bit as the single atom of the entire digital universe. But okay, how can you build everything we see on our screens with just two symbols? Well, you combine them. Think about how we count. Once we get to 9, we run out of symbols, right? So we add a new column to the left and start over to make the number 10. Binary does the exact same thing, just way sooner. 1 is just 1. To get to 2, you've run out of symbols, so you add a new column and it becomes 1, 0. 3 is 1, 1, and 4 is 100. With this simple pattern, you can build literally any number. All right, so we have our alphabet, ones and zeros. But an alphabet isn't much use without some grammar, right? You need rules to form sentences. For computers, that grammar comes in the form of a few incredibly simple rules of logic. First up, we have the rule called and it's super simple. The outcome is only true or a 1 if both of the things you're checking are also true. The perfect example is starting a car. You need to have the key and you need to turn it. If you only do one of those things, nothing happens. Next, we've got or. This one's a little more forgiving. With or, the outcome is true if at least one of the inputs is true. Think about paying at a store. You can use cash or you can use a credit card. Either one will work just fine. And the final piece of our grammar is the easiest one of all, not. This one does exactly what it sounds like. It just flips the input. If you give it a true, it spits out a false. If you give it an off, it makes it an on. Simple as that. And get this, these three super simple operations, and, or, and not, are the entire foundation of a field of mathematics called Boolean algebra. This is the language computers use to make every single decision. It's basically how they think. Okay, so we've got our letters, the ones and zeros, and we have our grammar, and, or, not. So what's next? Well, now we have to actually build something with them. Let's talk about how these rules become physical things called logic gates. So what is a logic gate? Think of it like a tiny little circuit, a miniature machine made out of components called transistors that's physically built to do one job. You have AND gates, OR gates, and NOT gates, and each one is a real-world physical version of those grammar rules we just learned. This is where the magic really starts to happen, when you start connecting these gates together. You can arrange them in all sorts of clever ways to do really complicated jobs. But there's a catch. If your design is too complex or messy, it'll be slow and inefficient, kind of like taking a bunch of back roads instead of the highway. For example, take a look at this. It might look like a random math equation, but it's really a blueprint for a computer circuit. And building it exactly like this would work, but it would require a lot of different logic gates, making it clunky. But using those rules of Boolean algebra, a clever engineer can simplify that whole thing, down to this. Now here's the amazing part. This new design does the exact same job and gives the exact same answers, but it's way cleaner and uses fewer physical parts. And this process, this simplification, is the secret sauce of modern technology. It's not just done once. Chip designers do this millions and millions of times, and that's what makes our phones and computers get faster, cheaper, and more powerful year after year. All right, we've gone from the tiniest switch all the way up to logic gates. Now let's zoom out, way out, and see how these tiny little building blocks come together to form the powerful processors that are the heart of everything we use. It's really like building with Legos, just on a microscopic scale. Everything starts with this single bit. You use logic gates to do things with those bits. You combine gates to make simple circuits, like one that can add two numbers. You group those circuits into bigger, more complex units. And eventually, you put all of that together to create the processor, the CPU. And that CPU, well, that's the star of the show. It's the brain of the whole operation. It works with memory to store information, and with input and output devices, like your keyboard and screen, so we can interact with it. But the brain itself, the part that does all the heavy lifting, is built from nothing more than those simple logic gates. Now, the real engineering marvel is how we cram all of this stuff onto one tiny piece of silicon. Over the years, we've gotten ridiculously good at it. We've gone to what's called very large-scale integration, which is a fancy way of saying we can pack not just thousands, but literally billions of these logic gates onto a chip no bigger than your thumbnail. So, let's bring it all back home. That simple on-off from a light switch gave us the ones and zeros. The ones and zeros gave us our rules of logic. The rules of logic gave us physical gates. And when you put billions of those gates together, firing at unbelievable speeds, you get everything. Every app you use, every photo you scroll past, every game you play, it's all just a storm of simple switches following very simple rules. Isn't that just mind-blowing? All the incredible complexity of our modern world, all of it, springs from the simplest possible idea, on or off. It really makes you wonder, doesn't it? If we've managed to build all of this from a simple switch, what on earth are we going to build next?